Okay, good evening to all the students. Good morning to both the professors. We welcome you for the final and fifth day of our collaborative teaching on multi-core computing and open power architecture. We have experts Dr. Gokarna Sharma, Kent State University, as well as Dr. Arjay Kusum Das from University of Wisconsin. Both the expert has done excellently well for delivering the content. So this is the final day where Professor Sharma will be giving us the details about the IBM Power 10 processor chip summary and the architecture and the details. And if time permits, he may give us a little bit idea about the processor design and HDL. So it is all up to him and the students' interest how we go for in this particular session. Thank you all for joining, and I hand over the session to Dr. Sharma, please.
Thank you, Dr. Gazar. Welcome, everyone. So towards the end of the lecture today, we're going to do multiple choice questions as well. We prepared. Dr. Das will take care of that. So I would like to cover as much as possible. And then if I'm not able to cover something, then as I promised yesterday, I'm going to share the slides on those topics. Okay, so you could consult them. And then after that, if you have any questions or if you want to talk to me, then we can definitely talk offline. So today, I start with Power 10 processor. So the whole goal of talking about Power 10 processor is to know what are the different design points that the chip manufacturers take into account to avoid or minimize different bottlenecks. For example, yesterday we talked about number crunching. We talked about memory bandwidth. We talked about interconnection, right? So when you move data, then you have to be able to move data very fast with minimum latency. So if you improve on one aspect of that, and then if you are not able to improve on something else, then as a whole, you will not be able to get the benefits. So the whole idea is to optimize in each and every aspect that is possible or that comes into picture for the processor, right? And then in Power 10, not just they are trying to improve on the laptops which have Power 10, and then you just run that laptop and then you are working, right? So they are looking more into what if this Power 10 processor becomes a node in a bigger computer. Let's suppose you have a supercomputer that you build using Power 10, and then what are the features that are available in Power 10 that makes this interconnect easy and everything. Okay, so today we'll go with these numbers. Today we go with these technologies. We might not be able to, as I mentioned before, we might not be able to dive into all the details of these different technologies, but what we do is that we introduce these technologies. We will get to know in very high level what these technologies mean, and then we'll see. So this is the Power 10 processor chip. If you see here, the figure tells everything actually. So you have here in this processor, you have 16 cores. So you can see here the top row, and then after top row there is a cache region, local cache plus L3 cache. The second row here, this particular row here, okay. And then after that, again, you have two rows of these processors, and then you have L3 cache, and then you go into the bottom row where you have 4 cores, okay. So these cores have 2 megabyte L2 cache. Okay, they have private L1 cache, 2 megabyte L2 cache. L2 cache is also private, as you can see from there. And then L3 cache is shared. So the bottom L3 cache, 64 MB, is shared by the bottom 8 processors, and then upper L3 cache region is shared by upper 8 processors. Okay, so this technology was developed by Samsung. So the whole area is 602 millimeters square. This is 7 nanometer. So it has 18 billion transistors in this particular processor chip. Okay. There are single chip or dual chip sockets. So we'll talk about that. How do you connect these processors to each other, and then how do they communicate? So there are different ways to do it. So in next maybe a couple of slides, we'll see what does it mean by single chip or dual chip sockets. So if you look here, so the middle part says the processors and everything, and then if you look into the side vertical, rows there, you see that SMP, memory, accelerator, cluster, PCI interconnect. So everything is there. That those features are available there on the side, so that you could have, if you connect it to other processors as a cluster, or how do you communicate outside to the input-output devices? So you have this PCI interconnect. And then how do you connect to memory? So everything is there. That infrastructure is built there. And then if you look to the boundary, then you have memory signaling. So you could see on the both sides, memory signaling. This is 8x8 open memory interface. You could see that. You have PCI signaling here on the bottom side. You see power exon, so that is on the kernel. So this is how it is designed, this particular processor chip. And then if you look into PowerPC processors like Power 10 or Power 9 and Power 8, somehow they are designed like this. Okay, you will see some variation of how the L3 CAS is managed, how L2 CAS is managed, how the connection is managed. So let's talk a little bit about the computational capabilities of this processor. So if you look here, it has 15 SMT8 cores. Okay, so 2 megabyte L2 CAS per core. So you see that L1 CAS is definitely smaller than L2 CAS. So each computing core has 2 megabyte L2 CAS. So they have a very small, maybe 64 kilobyte or something L1 cache. And then you see that L3 CAS is shared L3 CAS, and then it is 64 MB, huge amount compared to private L2 CAS. So what is private and public CASes? Private CAS means private and shared CAS. So private CAS means the processor which has the CAS is not shared to others. Shared CAS is shared to others. So you have to deal with the CAS coherence protocol there when you worry when you are working in this environment. So you have 15 SMT8 cores. So what is SMT8? SMT8 means you can have, each core can issue up to 8 hardware threads. Okay, that's what the SMT8 means in this processor context. And then you have up to 15 SMT8 cores. Why up to 15? You could see that there are 16 cores. Here 16 SMT cores, because in each row there are 4, but somehow in PowerPC setting, 1 core is not used for computation. Okay, so that's why they say up to 15, although there are 16. So 1 is reserved for different reasons. So up to 120 megabyte L3 CAS. Okay, so you see load latency, and then you have non-uniform cache management is there. Energy efficiency is 3 times compared to Power 9. So they run the experimentation, and then against different benchmarks in Power 9 and Power 10, and then they measure the efficiency. So these numbers might be a little bit optimistic, because the document is from IBM, so optimistic, but if it's not 3 times, maybe it's somehow 2.5 or 1. Okay. So we'll talk about what does it mean by enterprise thread strength optimizations. We'll see. It has also AI and security focused ISA editions. So there are different instruction sets. They try to deal with the problems related to AI and security. And then you have the matrix multiplication power that is improved compared to Power 9. For example, for general matrix multiplication, it's 2 times improvement, and for SIMD it's 4 times improvement. Okay. And then you have the L1 CAS. So and then you have 4 times the memory 4 times the memory management unit relative to Power 9. So the improvement there. You have open memory interface. You could see open memory interface on the top left column, or no, the left column or the right column. You could see there. So 16 times it, the signaling that is used, the open memory interface, and then it will give you up to 32 giga, 1 terabyte per second data transfer. Okay. So the latency is minimized, for example, per different contexts. So compared to Power 9. Similarly, you have Power Axon interface. You see on the the 4 corners. So again, it could provide 32, 1 terabyte per second, the bandwidth for that. And then you have SMP interconnect for up to 16 sockets. So there is open CAPI attached for memory, accelerators, and input output. Probably Dr. Hofste will talk about open CAPI today when he delivers his lecture at 9. So, and then you have integrated clustering. So there is a clustering feature that is there. So you could cluster memory, and then we will see the benefit of clustering memory. So if you have different workloads, and then when you run these different workloads, then how do you put them in memory? So there is a way to put them in memory in such a way that you can share the memory and you can use the memory from other processors too. Okay. And then you have the interconnect PCI per input output. So again, it delivers up to 1 terabyte per second bandwidth for that. So this is the socket composability. So single chip module and dual chip module we talked about. So here, if you look into this one, the upper part is up to 16 single chip module sockets. So these sockets are how these cores are connected to each other. So if you look here, each core is connected to vertical. So in a row, one chip is connected to everyone else, right? And then vertically too. In a column, each chip is connected to everyone else in that column. If you see here, that's the single chip module. Okay, this is how you are connecting. So particularly if you are in a row, and then if you are in a column, then you are connected to all the other processors in that row and in that column. Okay, so this is how they are connected in single chip module. So in single chip module, so every processing core is connected to other cores there. So basically, in a row, you treat the processing core individually. So you have one core connected to all 3 others in a row, all 3 others in a column. Okay, the same column. If you talk about dual chip module, then this is how it works. So you consider 2 cores in a row or in a row together. So you are considering them together, and then now you are connecting them. When you connect them that way, so here if you see, this is how the connection is done. So basically every one is connected to every other here. And then if you look into this 4 Lyceum sockets here, so you have the top left cell, which has 2 processors, and then the other top right cells, 2 processors, and then they are connected within each other. They are connected to the on a row to all of them. So you see the connection here. The connection here is that in a row, the left in the top left one, the right one is connected to the left one on the other side, and then you are connected to vertically to the processor's bottom and all. So here you could see the more connection. So when you have this more connection, you could get the throughput that is better than the single chip module throughput. Why throughput? Because here the connection provides you to be able to transfer data very, very fast. So here, if you look into the throughput per socket, the way you design the socket in dual chip module, then you can have up to 30 SMT8 cores, and then you could have the benefit of memory transfer that is 128 times 32, 1 terabyte per second. That's how the compute and IO density you can get. So from the connection, you can already see that how much the benefit that you get from the dual chip module compared to the single chip module. And then if you need to transfer some data from, let's suppose, this particular chip on the bottom left corner to top right corner, then there is a certain way you have to transfer data. For example, from the bottom left, either you go on the horizontally top to the top left one, and from top left one directly connected to the right one, right? So you will have a shortcut here, okay? So the fastest possible is you have one intermediate node, and then you can go to the destination, and then you can have, if that path is not available, then you have an option to pick maybe 2 intermediate nodes, and then you could reach there. So you have more flexibility on. At max, you will pick 3 others in a row and 3 others in a column, and then eventually you will reach there. That will be the longest path for per core to send communication to other core. Okay. So system composability. So here, the open memory interface edge are here, the yellow vertical vertical lines that you see here on the rightmost figure. So where the open memory interface edges are. Okay. So so it provides the bandwidth, more better compared to the DDR4 signaling. So there is a way on how do you signal, how do you get data from memory and then write back data to memory. But anyway, here here the improvement here, this is done in OMI, makes memory bandwidth even better compared to Power 9. Similarly, on the left figure, if you see the Power Axon corner that you see here, the yellow ones, then if you look into this one, and then in the middle figure, if you look there, the Power 10 chip is in the middle. So you have OMI memory, the bandwidth that is provided is 1 terabyte per second. Okay, and then Power Axon 2, it will provide the bandwidth of 1 terabyte per second. So basically, it doesn't matter which way you connect, from the Power Axon, you connect to other different devices, and then whatever connection that you do with Power Axon and then OMI to the memory too. So you will get the benefit of memory bandwidth 1 terabyte per second. So this is higher bandwidth. And then they also work on minimizing the latency. So compared to Power 9, so it has lower latency, high bandwidth, and then they have also signaling technology that is better than the previous ones. So here, this is how this particular technology works. So for system enterprise scale and bandwidth, so you have simultaneous multiprocessing and main memory. This is how it is working. If you hear the Power Axon, so you have SMP interconnect. This is how the interconnect is working here for the single chip module. So here, this interconnect. So you can build up to 16 single chip module sockets, and then you have high bisection bandwidth. So here there is a notion of bisection bandwidth because you can partition, for example, go and then try to equally divide this this particular topology into 2 parts and try to see how many edges cross from one side to another, right? So that number, if it goes high, then we call it high bisection bandwidth. So bisection means you divide into half, almost half, or exactly half in certain situations, and then you want to count the number of edges that cross this these 2 parts. Okay, and then if that number goes high, then there is high bisection bandwidth, and then this high bisection bandwidth, what it does, it tell is that from one side there are many different ways of communicating to many different communication links to communicate to the nodes on the other side. And then if you have this bisection bandwidth high, then you know that you can achieve, say, fault tolerance. You can also deal with congestion, because you might find different ways to route a message from one side to another side. And then here, so OMI memory interface will connect to the main tier DRAM. So it's here. So and then here, so they particularly have the not DDR4, the newer version DDR5 DRAM memory with. So this DDR5 is improved compared to DDR4, so that it will provide higher bandwidth and higher capacity. And then the higher bandwidth means, let's suppose you have a technology that can go and communicate to the memory, and then memory has to also support that higher bandwidth and then be able to provide the necessary data back to the interface, so that it can be transferred to the processor. Okay. So yeah, so that's why this bandwidth is improvement, and then 1 terabyte per second is a huge huge bandwidth, and then so this helps. So that's why this bandwidth helps when you are doing some number crunching. So in number crunching, you are reading and writing huge amount of data from memory to the processors and then back, right? And at that time, it helps. You could do you could transfer more data per second. So again, you have data plane bandwidth and capacity. For example, if you look here, open memory interfaces, then you can connect to many different classes of memories. For example, here, higher bandwidth, ZDDR DIMM. So this is the memory here, main tier DRAM memory, storage class memory. So you have many different memories, and then you will be able to connect to this different kind of memories. Similarly, here on the left side, we see the SMP interconnect, and that this interconnect is able to transfer data very fast. So so open memory interface attached storage class memory can provide high capacity encrypted persistent memory in a DIMM slot. Okay, so here we talked about it supports persistent memory as well, right? Persistent storage and everything yesterday. The Power ISA, it supports that. So these ones are, since it's supported, then the architecture itself has to, or the chip itself has to have the hardware technology so that you could run these instructions, right? So here you have this storage class memory, and then you have the necessary instructions and everything, and then the technology to be able to support this bandwidth here, and then do the high capacity communication to storage class memory, and then also be able to do the necessary to run necessary functions, and then the necessary the method to be able to store data to the storage class memory. Similarly, you have OpenCAPI. Dr. Hofste will a little bit talk more about this one, the OpenCAPI. So you could see here from this one, OpenCAPI attached. For example, here you have here OpenCAPI on the left side. You could see here. So you can have accelerated application. For example, application is specific integrated circuit or field programmable get arrays, whatever. You can have actually this OpenCAPI technology. It attaches FPGA or ASIC based accelerators to this power 10 chip. Okay, and then so this OpenCAPI helps to achieve high bandwidth and then also achieve low latency when you connect these accelerated applications, ASIC or FPGA, to the power 10 chip. So here, so this one, so this OpenCAPI attached particularly helps to somehow extend the bandwidth that you have. Here you have power Exxon, and then 1 terabyte per second you support up to this point. Then OpenCAPI supports that, somehow extends that bandwidth to be able to to be able to provide this high bandwidth to FPGA or ASIC, accelerated apps that you connect to the power 10. So here again, you have a storage class memory, as we mentioned before. So it provides high capacity, and then the persistent memory storage for the Power 10. Okay, so there is a pod composability. So we talked about memory clustering, right? You could see here, you could actually cluster a memory here. So if you look into the top left part, there is a way on how can you cluster memory. So the PowerXon memory clustering works like this. So if you look here, so you have this this memory. So basically what you do is that there is a capability that enables a system to map another system's memory as its own. So you look at the another system. So you have this the connection, so PowerXon connection, and then that goes on and then looks at if you have a memory that is there in another system, so you can map it as the memory in your one system. Okay, so basically when you are able to map that, then what you can achieve is that you can actually cluster. So let's suppose there are different systems, different the competing cores that are processing cores available in different parts, processing nodes, and then they have their own memory. Now you can actually go map that memory and then cluster that. Okay, so multiple systems can be clustered, sharing each other's memory. So here, and then you can also provide the communication similar to this single chip module kind of connection that you did. Here, if you look here, again, you have rows and columns. So in each column, the memories are communicating with each other. You see the vertical lines connecting them. Okay, they have the connection in each row. Each node can communicate to the next one on the top and next one on the top and so on. You can go like that. Again, on the row, you connect from one row to one node in that row to another memory system in that row, and then you continue that way. So again here, since you have this grid-like setting, then if you need to send from, let's suppose, bottom left corner to top right corner, you know how many other systems that you go through. Okay, so this is how you could do the clustering too. Okay, so this clustering facility provides you to do many other stuff. So for example, let's suppose you have different workloads, and then you have to map the workloads, and then how are you going to map these workloads to the memory, and then sometime to be able to store the workload and then provide enough memory to the system also helps in expediting the process. So for example, here, this is what it does. Let's suppose workload A is running here on the top. So we are talking about memory clustering. Okay, so here we are talking about disaggregation as well as sharing of distributed memory. So this is the use case. Let's suppose you share load store memory amongst directly connected neighbors within pod. Okay, so unlike other schemes, memory can be used as low latency local memory, as non-uniform memory access latency remote memory, right? So you have local memory. So when you have different processing nodes formed using Power Core, then you can have local memory that is your own memory. And then, so that memory, whatever you do, you are going to access that memory with the same latency, right? You do not need to really worry about, when I access that memory, then I have more latency or not. So they have uniform latency. So when you have shared memory, just within, so everyone is sharing their memory, then you have the same latency, and then you can somehow neglect that latency. You can say that, oh, everyone is paying that latency, then I'm not going to take into account. But think about it. Let's suppose there are two nodes connected, and then they have their own local memories, and then one node sometimes accesses the local memory on its node, and then sometimes it accesses the memory that is not in the local node, that is on the other node. Then how do you deal with that? So this is, the local memory has some latency, and then the remote memory has some other latency that is higher than the local memory latency. So if you look into the research on that, so for the local memory latency is somehow negligible compared to the latency that you pay to go and get from the remote node. And then what you can do is that, so basically the computation or the cost on latency is dominated by this this Nirma latency. Okay, so that's why you have low latency local memory, so that you can really not take into account this low latency because it's very low, and then everyone is paying that that latency when they are executing locally. And then you have the NUMA latency. This NUMA non-uniform memory access comes because in local node, when you access the memory, you have you have one latency, and then when you go to the remote node and access the data, then it has different latency. So that's why the latency is non-uniform. And then if you have more nodes, then what happens? Let's suppose it depends on how far the other node is. So for example, that node has to be visited through some intermediate node. And then when you have to visit going through the intermediate node, and then you reach to your destination node, then you are paying even furthermore latency compared to the node that is your immediate neighbor. You have direct connection there. So so that's why the non-uniform memory access term that comes into picture. So for example, here in this example, so how can you share this memory, right? So two directly connected neighbors within the pod. So we talked about what the pod is. So you can have the clustering and everything. So here, the example here, what it shows is that the pod, let's suppose we have a pod, 8 systems, each with 8 terabyte of data, terabyte of memory. Okay, so you have this pod, you can see here 8 systems here. Okay, now there are 3 workloads, workload A, B, and C. So workload A has a requirement of 4 terabyte low latency. Okay, so since the requirement is 4 terabyte low latency, probably what you want to do is that to achieve this low latency requirement, you do not want to assign this job to 2 or more nodes, because if you assign that to 2 or more nodes, then you have low latency on one node, and then you have higher latency on other node because NUMA comes into picture, and then you have a problem, right? So to achieve low latency, you want to probably assign that job to only one system. Okay. So there is a workload B. The workload B has the requirement of 24 terabyte, and then it has relaxed latency. So basically for B, since it has relaxed latency, you can actually assign that workload to any node in the pod, okay, any system in the pod. Let's suppose workload B is here in the second node, and then eventually you assign that into any node that is available in the pod. So you have, because of the relaxed latency, so you do not need to worry about latency here. Now you have workload C. Workload C has the combination. So this is the mixed combination on latency and then the relaxed latency. Okay, so for example, workload C requirement is 8 terabyte of low latency plus 16 terabyte of relaxed latency. Okay, so 8 terabyte of low latency, that means you have to be able to store, have to assign this workload to achieve low latency for 8 terabyte. So probably you want to just assign it into a same node or the same system so that you will achieve low latency. And then for 16 terabyte, you can assign it wherever the, whichever system is available there. Okay. So here in this requirement, if you have the system, let's suppose we have a pod, and then the pod has this this setting here. If you look here, and then the pod. So for workload A, since it has 4 terabyte low latency, then you are assigning on the topmost system. So A, you see here. So let's suppose the every here. So this every node shows 1 terabyte. Okay, so that's why you have 4 terabyte here. So you assign to the same system. So you achieve low latency. Per C, look at the third system where you assign 8 terabyte to that node. or that system, so it will achieve low latency there, so the demand is met. And then for 16 terabyte, you assign to the 5 other systems that are on the bottom side. So you have 3 on one, 3 on other, 3 on other, 3 on other, so 12. And then this is 13. And then in workload B, you assign CCC. So that is 16. Okay, so the workload C. So when the workload C is assigned on other nodes, then you have this relaxed latency, right? So the latency is different depending on which system the task is mapped to. For workload B, you have all relaxed latency, so you can assign anywhere. So you decided to assign it to workload A, and then the top system, and then the bottom 5 systems you assign in this way, and then to have the 24 terabyte, okay, and then the relaxed latency requirement. So here, this is just one of the configuration that meets all the requirements of these different workloads, using this pod, the memory clustering, and then you can map, okay. So in Power 10, you have 2 petabyte memory size that enables much larger configuration. Not just this is one of the smaller configuration. If you want to go with bigger configuration too, it provides much larger one. So Ambika is asking any advantage of single chip over dual chip. So the single chip, I mean, it's just a configuration. It will be easier for you to do the communication, but somehow the latency goes high, but simple in design. So the design is going to be simple because whatever support that you do, it has to be written in hardware. So maybe for the dual chip, you need a little bit more processing requirement. You have to store the information in a way. How are you connecting? So the support, because you are connecting to connecting them as a cluster. In single chip, it is easier to do that mapping and everything. So maybe dual chip is better if you have too much communication. Let's suppose you have a workload which has not much dependency. Okay, so you are running a parallel workload in Power 10. Different processors are running that workload on threads, and then there is no dependency. Let's suppose the dependency means the workload that you run, or the part of the code that you run in one processor and part of the code that you run in another processor. Let's suppose they are not sharing any memory data, or they do not have any dependency on the data they use. Then the single chip is okay too, because you are not going to do the interconnect communication. You are not going to communicate with the other processor processing core to deal with the dependency. Okay, but if you have too much dependency, then probably this dual chip module will help to minimize the latency there. Okay. Okay, so memory clustering can go further than the pod. So this is enterprise scale memory sharing. So here, if you look here, you can come up with different kind of connection modules. So for example, here, pod of large enterprise systems. Here, distributed sharing at petabyte scale. So if you look here, there is a data, and then the connection you have. Every node is connected to every system node is connected to every other. If you see here, so it has how many? 1, 2, 3, 4, 8 systems. And then if you look at, everyone is connected to all others. Okay, so this provides more, this minimizes the latency, and then you can share data to others in bigger amount, like with more bandwidth. And then here, when you are able to share this, then the latency is going to be minimized because you have direct connection to any other system that you want to communicate. Similarly, you have another one, depending on the application that you run, depending on the communication between these jobs or the workloads that you execute. For example, here, hub and spoke with memory server and memoryless compute nodes. So here you have compute nodes and then the memory servers. So here the connection is going like this. This is kind of a star kind of connection. If you see here, the connection is going from one node to these other nodes. And then so the compute nodes are not connected to each other. They all are connected to the servers in the middle. Okay, so you can have this hub and spoke kind of connection as well for the clustering. So similarly, you have pod level clustering. So you have clustering in the pod level. So for example, here the use case low latency, high bandwidth message scaling at thousands of nodes. If you see here, so how do you do the clustering? You can do this way. So you can connect the systems as we saw before here. This is similar to the picture that we were looking here. I think next one. Here, this top left figure that we're looking at, this is what we are seeing here more. So here, how do you communicate? Let's suppose you have a sender somewhere, and then you have a receiver. Then the way you could send is, this is the shortest path that you use to send to the receiver. So from the sender, look at the lines that are blue covered by yellow. So if this is the sender system and then you go into the receiver system, then from sender you can go horizontally, to the row, to the column where the receiver belongs, and then you can just go from the go transfer, doing the communication and reach to the receiver. And then if you look here, this horizontal connection is just from one row you are connected to the system in the next row, and then you continue that way. But in vertical, there is some kind of connection happening where you see, so you are skipping. So you have two connections. One is, so if let's suppose you are skipping one system here and then connecting just the 2 hop away, the 2 hop away neighbor, you are connecting here using one connection, and other you are just using other connection. So this is like one connection skips one and goes to the next, another connection skips that and then goes to the node that was skipped in the other connection. So this is to also minimize the bandwidth, or somehow remove the limitation of this connection on the latency and the related setting of minimizing the data transfer latency. So system composability. So if you look into, so we looked into this interconnect here. We looked into OpenCAPI, and then how does it help to connect FPGA and ASICs, and then you have this integrated memory clustering we looked at. Now here, this PCI, the interconnect for the input-output devices. So you could see here, you can have this connection here. It also provides the input-output attach in similar scale, like almost 1 terabyte per second bandwidth, this PCI. And then this is also improved from the previous versions of power processors to this processor. Okay, so the socket performance gain. So they were comparing here the baseline. So baseline is the power 9. So what is the performance gain in the power line? So here the power 9 baseline. So you can have 1 because that's the baseline. So you normalize that to 1, and then you want to see compared to this normalized one, how much you benefit that you get in power 10. Okay, so in power 10 integer, the socket performance gain is 3 point sometimes. Okay, so improvement. Similarly, for memory streaming, you can see here, if you use the for the memory streaming, if you use the DDR4 open memory interconnect memory, so the DDR4, if you use it, then you will get the benefit up to 2 point sometimes. And then, but if you use DDR5 newer version of that, then you will get more than 4 times. Okay. Similarly, you have for floating point and others, the benefit that goes 3 times. So that's why in the first slide we were claiming that the system is 3 times better for the floating point. So here, this is the enterprise strength plus AI infused. So if you look into this SMT core, so one SMT core, this is what it looks like. For example, you are providing new prefix architecture. So we talked about prefix architecture yesterday. So this is the prefix architecture where it provides more flexibility on the system. We have a SIMD that is optimized, for example, 4 times the metric SIMD. So that is bigger and better. Similarly, they provided 2 times the load capability, 2 times the store capability, and then 4 times the L2 CAS, so in one core. And then they also improved on the control and branch instructions. Okay, so these improvements are compared to Power 9. Compared to the capability in the Power 9, for example, the load capability in Power 9, so this is improved 2 times. Similarly, stored 2 times. Similarly, like a SIMD, general SIMD computation, that is 2 times efficient, right? Similarly, metric SIMD, that is 4 times efficient. So in the microarchitecture, you have up to 8 threads per core, right? So SMT8, that's why 8 threads per core. And then you have 240 per socket. You can have up to 240 per socket. So you can have up to 240 because in each socket, you can have either 30 SMT8 cores. Okay, so if you put them together, then you will have up to 30 SMT8 cores or up to 60 SMT4 cores. Okay, so why 30? Because if you put 2 power 10 chips per socket, if you put 2 power 10 chips per socket, then you have 15 processors you use. One you are not going to use, the that we talked. So in 50, if you have SMT8, then it is going to be 120 threads. And then since you are putting 2 power chips, then that would be 120 times 2. So that's why we say 240 threads per socket when you have 2 power chips that are put in one socket. So either there will be one power chip in one socket or up to 2. Okay, so that and then you can also have 60 SMT4 cores. So the SMT4 means one core can ECU up to 8 threads. Okay. So optimized for performance and efficiency. So almost 30% improvement on the core performance, 20% improvement on single thread performance. So that means the core itself is stronger compared to the previous Power 9. Even if you are running the sequential jobs. Okay. So the core performance efficiency improves 2.6 times, and then in each socket 3 times. So also we talked about AI infused. So this is particularly the system is getting better going from Power 9 to Power 10. And then you have new instruction set architecture with AI data types. So for example, there are different kind of data you have to deal with in the AI related application. So the new instruction set architecture is made more flexible so that even if you have different kind of data types, you can handle them. So similarly, powerful core, you have enterprise flexibility. So for example, here, different software stacks that you can support, for example, Power VM, so the virtual machine, and then all that. So there are different ones, for example, Linux and Power, IBM I. So these all software stacks can be supported here. Partition flexibility and security, for example, you can have thread level partitioning, and then thread level logical partition scheduling. So you can say that when threads are running, you can logically partition the area of memory so that the thread can use that. So, and then you can schedule based on that logical partition, so which helps. Similarly, they have hypervisor, and then they have hardware assisted virtual machine isolation. So they have there's more flexibilities provided on the security and other areas. So here, the workload is also balanced based on the hardware. For example, here, if you look into the instruction cache, so the top figure, if you look into the instruction cache, then the instructions will come from there. Omega, they can be connected. It depends on, for example, if you connect to everyone else, then there is a difficulty on, like mapping that connection in the processing chip. So you have to basically, in the circuit chip, you have to draw that, right? And then that complication arises there. So there is a complication on how you write these routes or the connections in the integrated circuit as well. So there is another challenge that comes into picture. So the hardware-based workload balance, for example, if you go into instruction cache, then you have instruction buffer. So instruction cache is used to store the instructions. So, and then you have instruction buffer. And then from instruction buffer, there is a way. So this hardware here that you see, this hardware line here, that will somehow balance the workload to provide to different execution slices. So we have the slices here. If you look here, slice 1, slice 2, up to 8 slices. And then you can divide the workload into these slices and then balance the workload. So balance the distribution of the instructions to these slices. So when you have these 8 slices, then you can compute faster, right? Because you are doing parallel. And then also after these instructions are provided to these different, assigned to these different slices, then you have the load and store units. They could also try to load faster from here. Okay. Similarly, thread resource balancing too. You can balance the thread resource. Similarly, you say that the workload is balanced, you can also balance the thread resource here on how much whether the resource needed for that thread is available for that or not, and then so the hardware deals with that. So here, as we talked yesterday, so the Power10 implements Power ISA, okay, so version 3.1. So we talked about some of the features yesterday. So this is just the recap of that. For example, prefix architecture you have. So this prefix architecture helps to greatly expand the opcode space, and then the MMA masking, and then other benefits. So MMA is matrix multiply assist and all that. So you can see that when you have the 64-bit architecture, then you can also do you can actually try to try to signify what do you mean by trying to do something, depending on the bits and then the information that you put there. Okay. You have new instructions and data types. For example, new SIMD instructions. you have new instructions for control flow and everything. For example, here you could see, you know, you have permutation, extract, max generation, bit manipulation, matrix math assist, and these instructions are new. Although they are optional, but they were added. For example, in Power 9, they were adding transactional computation kind of instructions. Okay. Advanced system features and ease of use. You have storage management. For example, you have persistent memory storage management. So when you deal with the persistent memory, then you have to worry about plus. So the plus is after you do the computation, then you ask it to write to memory, then you have to wait for that to be written before you can write from there. So you have to somehow sync on the previous computation was written in the persistent memory, and then the original locations were updated. So so this plus is the method that takes into account all the background aspect of how you update the memory after some computation you do, and then it has to be written in those locations. Similarly, debug, you have copy paste extensions. For example, you have memory movement, how do you move memory and all that. Okay, so definitely if you go and look into the specification document that is more than 1500 pages, you will get to see all the details on these features, and then the whatever features they were there in Power 9. So this is the security for the enterprise cloud. So they provided here, you have VMs, you have applications, you have services that is from the cloud, and then you have containers, you have different software stacks there. And then you have the virtualization capability, that is the secure virtualization. So if you hear this is nested, so on top of our VM, then you can have a virtualization, and then from there you can go into processor security and foundations. For example, the crypto performance, right? So the crypto is a big so you have a crypto performance, for example, core crypto improvements for today's algorithms. For example, SSA3, SSA256, and others are the algorithms they use in proof of work. They use in different kind of the crypto mining and everything. So they have to be computed faster, because they have to be computed faster, and then there is also the security involved, right? So you should not leak anything there. So so that's why they already put those improvements on those algorithms so that you could compute faster. And then also there are new algorithms that you might use in future, and then they are also providing support for that. And then also you have the memory isolation you have to deal with. So this memory isolation is, if you need to do the secure computation, then you have to have this trusted hardware scenario, right? So we're talking about trusted hardware is some part of the memory or some part of the some part of the system. If you go there and then do the computation, the hardware itself provides the security guarantee. The whatever information that is there, you cannot just access from outside. You need some authority to that. So that is also the feature that is available here for that security. So you have this core microarchitecture. So this is very powerful. If you look here, this doesn't look very simple, but you have improved fetch and branch predictors. You have instruction effective addressing. So you have L1 instruction cache. You have you have a predecessor code and everything. You have this information. You have instruction buffer, instruction table, You have decode and then others. For example, you have different execution slices here. Only 4 slices are shown. Actually, you have 8 slices. You have L1 data cache, you have L2 cache, you have L3 prefetch of data. So L3 prefetch, it does 48 entries to that. You have translation look-aside buffer. So there are load queues, load misqueues, prefetch, and there are many different these improvements that were done to be able to improve. So you might say, okay, what is the benefit of this individual improvement? So there is a context that there is a bottleneck, there is a problem related to not having this and that, so they were improving. For example, the green ones, the green boxes, they were improved compared to Power 9. The blue boxes, they are improved in such a way that they give at least 2 times better performance in the new system. The red ones, it gives equivalent to 4 times. So you have a 4 times improvement that is done on the capacity. Okay, so the capacity is improved at least 2 times, exactly 4 times. For the translation look-aside buffer, L2 cache, they improve the capacity 4 times. For the blue ones, they improve the capacity at least 2 times. And then for others, they improved, not by 2 times, but some factor. Okay. Similarly, you have MMA accelerator that is 4 times bigger. So you could see here the improvement that helps to get better performance. For example, double SIMD, large working set, right? So when you increase the capacity, then you have a large working set. Deep, wider instruction windows, okay? Deep, wider instruction windows. You go into data latency, so you want to minimize the latency. For example, L2, L3. So here, L2 latency is 13.5 cycles, so that is improvement. L3 is 27.5 cycles, that is improvement. Similarly, translation look-aside buffer, so there are data latency improvements compared to Power 9. Similarly, you have branch, you have improvement there. Similarly, you have fusion. So for example, you have SIMD, merge and back-to-back. So you have load and store. For example, you have the consecutive storage. The fusion is you want to do load and store individually, or somehow you put different operations together and then try to do it at the same time. What do you mean by estimated?
I think she is trying to tell that how you are measuring that it is improved by 2 times.
So compared to Power 9, the capacity they provide is 2 times more. For example, the size of the translation look-aside buffer, if it was 2K, now they made 4K. It's like that. So you are improving on the size. So that is not on the execution efficiency, that is on the capacity. So when you have more capacity, the goal is that probably it will give better efficiency, okay? So when we talk about here, they have these results were, more of them, I will say these results were a little bit on the simulation side. They were doing the, experimentation on the simulation architecture, and then it came up with the results. So when you have this architecture, then it gives that improvement. After you have the Power10 processor, and then if you run the real workload, for example, there's a benchmarks, and then when you measure, then maybe you will get a little bit different results, but somehow on average, the time and performance results are okay. You will get that kind of benefit. So they have improved clock gating. They have microarchitecture efficiency. So these are the very small points. So think about it. So they are developing this power architecture for last 30, 40 years, right? And then when they go from one version to another, for example, they came from Power 7 to Power 8, Power 8 to Power 9, Power 9 to Power 10. They constantly looking at what is working and what is not working. So what is the limitation on getting better improvement, right? And then so that's why looking at that, they try to improve or add new feature, microarchitecture feature, so that it will help to offload the computation or make that computation faster. Okay. So here, so when they do that, then you will see how much benefit they are providing. For example, uh, here, so here the goal is to measure what is the performance that you are getting per watt of power that you spend. So here in multi-core architecture, this power envelope plays a big role. So what is the goal? The goal is that let's suppose you have let's suppose you have a smartphone. Okay, so you have a processor that you are designing for a smartphone. Okay, so when you design a processor for a smartphone, then what are you also looking at is what is the battery that you are putting for that phone. Okay, let's suppose you have the power, right? Or you have the power envelope. The power envelope is when the battery is fully charged, it will provide this much amount of energy, and then it will last for a certain time. Okay, so let's suppose what you want to do is that you want to have a processor that has the power envelope or 60 watt. Let's suppose power envelope of 45 watt or 60 watt. Let's suppose you fix that power envelope, right? And when you fix that power envelope, then what it gives you as a benefit is that when you fix it, and then when you have the battery, then you know that if you have a processor that works in that power envelope, and then you have some battery uh, of some capacity, then you know that smartphone will provide enough computation without recharge for at least one day or more than one day, or if you use it for a certain time, then you can go up to this one, right? So what you want to do is that now when you fix the power envelope, then you want to get the better performance. You want to compute faster and everything, but without spending too much energy. You don't want to go beyond this particular power envelope that you set. And then when you set that power envelope, and then you look into the performance, how much performance that you get in one system versus how much performance that you get in another system, and then you compare, right? So here, what they compared is that performance per watt is 2.6 times compared to power 9. So that means the system is more energy efficient. Okay, when you spend 1 watt, then the benefit that you are getting on the computation, on the improvement on the computation is 2.6 times compared to power 9. Okay, so that is one of the fundamental principle behind designing these multi-core processors, not changing the power envelope, fix the power envelope, and then if you could improve performance based on that power envelope, then that's it. That's the efficiency that you want to get. So that's why you call it energy efficient. It's very uh, you know uh, simple definition. There are other factors too, but this is one of the core idea behind keeping the power envelope fixed, and then try to optimize based on that, and then how much benefit that you get compared to the previous version. So again, you have this the bandwidth on accessing the caches and loads and stores and everything. If you look here, so you have a processor, and then you have 16 byte SIMD. So, and then you have the load, and then you have a store. This is 32 byte, and then L1 cache, 64 kilobyte. Okay. So, and then you have L2 cache, 2 megabyte, and then L3 region, you have 8 megabyte for each processor. So if you look here, then you are trying to improve on every aspect here. Okay, so for example, 2 times the bytes from all sources. So you can have, for example, open memory interface, L3, L2, L1 caches everywhere. You are improving here. Okay, so this slide shows what are the improvements and where you are doing. Okay, so if you look here, that's a more improvement. The bandwidth, right? So the capacity that you are providing, and then the bandwidth is increasing everywhere here. So they have 16 byte SIMD environment, and then this is providing the bandwidth because you are running these accesses in parallel. Okay. Similarly here, we talked about the accumulators. We have this, this MMA, the, metrics math assist. And then as we looked yesterday, so what is the, number of instructions you execute, and then the thread, and then the SMT8 core, and then how are you doing it? Okay, so for example, if you do the floating 64 bit, then you have X is 4 times 1, and the Y is, transpose of Y is 1 times 2, and then the accumulator will be of size 4 times 2 because the 64 bit extends into the accumulator, right? So, these are the kind of, results, and then what is the big plop that you could get per cycle when you do this kind of computation. So similarly, you have inference acceleration. So with the top figure shows the matrix math assist. So here we are looking at how do you do the computation. So we have n times m, n times k, and then k times m kind of metrics. And then when you multiply them and then add them, then you are going to get the m times n metrics. And then this is how the computation is done using the accelerator. Okay, so it shows the benefit that you get using the metrics math assist. Okay. Similarly, you have BSR, the vector scalar resistor architecture we have. And then you can also have dense math engine microarchitecture. For example, if you have too much number crunching, then you can have 32 byte loads. And then, this is the load history unit. So you have 32 byte loads, and then the vector scalar unit. So, and then here you have the operands. So you can just add them 16 byte plus 16 bytes, and then you have the accelerator. And then you can use this accelerator to speed up this computation. So here the Power 10 SIMD versus AI socket performance again. If you look into the Power 9 baseline, so you could see here the baseline is small. Power 10, if you run the LinPack benchmark, then you are getting 10 times improvement, performance gain. If you use Power 10 inference, for example, ResNet 50 floating point 32, then you are getting again the 10. ResNet 50, floating 16, then you have more than 15. Similarly, integer 8, ResNet, when you run it, then you'll get up more than 20 times. Okay, so this is the benefit they are measuring on this one. So this is a this is the analysis they have done before they manufactured the Power 10 server. But after they manufactured, when we run these particular benchmarks there, we might get a little bit, different results, but the discrepancy may not be very high. So, all right, so that's all on the Power 10 summary. Okay, so Dr. Gajser, would you like us to take a break?
Yeah, sure. We can take a break of 5 minutes. There are two things. That's what Dr. Das and Ganeshan was saying, that Peter wants to talk sharp at 9 and conclude at 9:30. So,
Mhm.
and feedback session also has to be taken. So I request you to conclude by 8:45 or 8:50.
That means
Now,
10,
now
that
you
means
have almost yeah, almost 30 minutes to go.
almost 30 minutes to go. Oh, that is perfect. Okay, let's do then. Let's do this. Take a 5-minute break now.
Yes, yes, yes. So we
Uh, uh,
start at, right now it is 8:18 here. So we start at say 8:24.
yeah, 8:24, and I'll go for around 20 minutes.
You can go
I
for
will,
30 minutes, also not an issue.
okay. So I will go for 25, 30 minutes. I will talk a little bit about microwatt and hardware design language, and then I will stop there.
Yes, yes, yes.
Yeah. So
So
okay, I will see you in 6 minutes.
yeah, yeah, please. Yes, Professor, welcome back again. You can continue for another 20 minutes or so.
Yeah, I will continue for 15-20 minutes, and then we'll have a QA session, and then
Yes.
we'll get ready for the later schedule. Okay, so I'll yeah, I'll try to cover a little bit the microwatt and hardware description language um, here. So what is microwatt, right? So microwatt is a tiny power core. So this tiny power core is written in the hardware description language. Okay, so this is not the hardware implementation. It's a simulation implementation, and this simulation implementation is open source. So you can actually see that it implements some OpenISA scalar subset. Okay, so basically it is a very tiny, so that's why it's a microwatt, right? It uses the base ISA scalar subset. Okay, so the base. So some of the some of the features, and then you can actually this is open source. You can go and then get this one, clone the directory from the GitHub. So there is a website, the link there. Here you can see in the slide. So if you go, you can clone it, and then you can see, you can compile. Actually, the description and everything on how to compile, everything is there when you go to this GitHub page. So this is open source simulation of the ISA. And then it also helps you to actually go and then try to modify that, or try to see how it was implemented, what is hardware description language, and then how you write in hardware description language, all that. Okay. So here, it's a single issue. So it is not a superscalar, it's a single issue. So you have one pipeline. So this is in order. It does not execute out of order, out of order instructions. It doesn't reorder. It's in order. So why that? Why single issue and in order? Because it aims to be simple and easy to understand. So you can just go and then get into uh, processor design. So basically this is the processor code, right? So processor code written in some language, right? Simulation. So aims to be simple and easy to understand. And then you can reuse from the open hardware world. You can contribute. There are many contributors to that. So if you look into this one, the single issue means you have a pitch that is implemented. You have the instruction cast, you have phase 2, decode 1, decode 2, execute, and write back. In execute, you can do multiplication, division, load and store, all that. Okay, and then they write back. Very simple pipeline, nothing big, nothing complicated. But this is the proof of concept that actually you can design it. Here, this is the GitHub page on this one. So as I mentioned before, this is written in hardware description language. I will talk a little bit about what hardware description languages are and then what they do. So there are many commits now, more than 1,000 commits on this GitHub page. So new functionalities are added. You could go and then look into the activity. Actually, you can contribute as well. If you come up with something, implement, and then go there, you can contribute here as well. There are many recent developments on this one. For example, ICAS, DCAS implementation, branch predictor implementation, interrupts implementation, translation loci buffer implementation, some Linux subset functionalities, and then it is continuously integrated. So you have new features added, everything. And then there are many community contributions, like the developers. They are interested in this open open power ISA, and then the benefits of it, and then who wants to design new processing cores, and then the development in this area. Here so when you want to integrate something into this one, then you have to have some test you have to run, and then it has to comply with that one, and then after it is successful, then you can integrate too. So this is actively updated, managed, and then so new features are continuously integrated. So actually, you can also do hardware reuse. Simple open protocol, widely used in the open hardware world, allowed to interface with the other projects. Actually, if you are interested in this one, you can go to this particular implementation Microwatt, look into it. Will also give you what was the motivation behind developing that one, what was what is going on now, what are the new features added, why you need those features and everything. For all of you who are in the advanced microprocessor architecture, you might find it useful. Okay. So open source simulation and synthesis. So for example, simulation is done using hardware description languages. Great environment for testing, including the including different including continuous integration, good language support, and then there is a maintainer who maintains all this GitHub directory and very responsive. Okay, so you can actually uh, do the FPGA synthesis as well using this one. Okay, so what I think is that you could go, and then when you look at it, you will get better better idea on what this is all about. Okay, so since I do not have much time, I will just leave it like that. So it can now support many different different architectures, and then the different particular kind of chips, the embedded in others. Okay, so here uh, this is part of a free open source software. Okay, we call it FOSS, and then EDA is the electronic design automation. So whole this goal of this free open software is that any software with source code is available for any purpose. It can be used, modified, redistributed. So that way it might ignite the new development in the processors and processing cores and everything. And then this is becoming more relevant because of these new embedded devices and everything that we are looking at, and then they are everywhere. Okay, so what is electronic design automation? Any software to help. Okay, so by automation, the electronic hardware designer. Okay, so any software that helps the hardware designer, then that software is EDA, electronic design automation software. Okay, so this is a vast domain. So let's clarify a little bit. So this is what it does. So you have a EDA. So the electronic design automation softwares, in these softwares, you implement the kind of a circuit that you want to build. Okay. So for example, printed circuit boards and integrated circuits, what you can do is before you make the chip or the manufacture the chip, you can go and then test your chip on writing the implementation in the electronic design automation softwares, and then you can somehow use the PCBs and others and gets and everything to verify. Okay, so these EDAs, what they do is that they somehow give you the implementation or the register level scenario, time-based scenario, or whether if you make an integrated circuit, if you manufacture a chip, whether it will work correctly or not. So you have to be able to identify the implementation is working correctly, right? So this helps. So here, what are integrated circuits? These are logical gates, right? So flip-flops and latches and memories and wires and some analog components, right? So these are integrated circuits here. So either you have to test everything in integrated circuit, or you have to test everything in the printed circuit board. But this is very difficult these days because of the complexity of the system that we design. Okay. So how are integrated circuits designed now? Not anymore by drawings. So early stage, very back in many years, we used to design by drawings. Okay, so it doesn't scale. It's still used for high level view, but not on the kind of a little bit going, dive down into all the situations, descriptions, and then how things should work and everything, what you intended to work, and then how, in fact, it works. Okay. So the use of hardware description language, so SDL. So these SDLs, what they provide is that although these are software implementations, how they will behave if you build, if you manufacture or integrated circuit based on the design that you have. So it'll give you very close, very close implementation, like as if you implemented that logic in the integrated circuit. Okay. So for example, there are different systems. For example, Verilog is a long developed hardware description language. Similarly, you have system Verilog, some changes that takes more into system aspect into view. Similarly, you have BSDL. The BSDL is you have BSDL. Is it, all right. Now, sorry about that. So BSDL is one, hardware description language. So the variation of all these ones here. Okay. So this is how the design flow works. So you have a hardware description language where you write the design, and then you run the simulation. After you run the simulation, then whatever design that you write, then you are going to check the design, whether it is working or not. Then you have a synthesis. That means you will generate a generic netlist of what you were trying to do and everything, and then you will map that. Okay, there's a target the specific netlist, what you wanted in the design and everything, and then place and route. So this is the physical implementation. In physical implementation, so when everything is set for the design, then you have to, in the integrated circuit, okay, this is how you are connecting these different components, different this net list that you have different features that you want there, and then you have to place them in the integrated circuit, and then the route, the communication, and everything. So here the hardware description language somehow helps you to write your design, and then the simulation that you do will check whether the design has some problems or not, whether it works as intended or not. Then you will do the synthesis, and then you will map them. You will target where you are going to put them and everything, and then place them out. So this is how the design flow works, and then you know where the hardware description languages are, and then how they help in this process. So again, we have integrated circuits, and then so for the integrated circuit, so we have application-specific integrated circuits, or field programmer will get arrays, and then we can, we can test the design here. Okay, so there are many languages. So if you look here, the hardware description language and simulation. So there are standard languages. For example, Verilog. You have Verilator, BSDL. So the hardware description language. So you have different versions of that. Similarly, you have waveform viewer. So you will see how the computation waveform is going on in the hardware level in your design. Similarly, you have verification frameworks. So you write the hardware description, you do the simulation, but how do you verify, right? So there are different, different frameworks to verify. So this is just to help the design process for the chip, and then they come into picture. So for the synthesis, again, for the front end, you use some kind of hardware description language, for example, ZDL or USIS or ODIN. So there are many front ends, okay? And then for the map, you have USIS plus ABC, and then you have place and route, for example, PPR, next PNR. So there are many this EDA tools available for you to do all that. Okay. So why you want to use EDAs? Because they are often free, at least for entry-level FPGAs. For example, there is a MakerSafe. For MakerSafe, it provides you an online IDE. You don't need to even install. You can go there, and then you want to, you want to implement some, for example, let's suppose the pipeline, 5-stage pipeline of ISA there. Then you can go and write code. So when you know in MakerSafe how you write it, then it'll just provide you all the functionalities, and then you can go and test. So this is maker chip, right? So before you build a chip, then you'll go and then write your design there, and then try to see whether everything is working correctly or not. Okay. So there is a whole ecosystem, and then you will have different stages, and then so you start from the hardware description language, you write your design, and then verify, compile, test all your design up to the bottom level, so that the only thing that remains is just go into making a chip. Okay. So so you have less price to test your implementation. Also, you can check for the performance. You can avoid vendor locking of anything. You can look into features. If some features are not working, you can remove those features or add those features. Support. You have flexibility, and then you can fix them very efficiently. You can change them, because it's not the the chip implementation, because if that chip doesn't work, then you have to come and then make another one. So there is a lot that you could do using these EDA tools, and then EDA tools are getting famous, and then there are new tools are coming. For example, one is the MakerSafe, and then you can use MakerSafe. It's like an online ID. You don't need to even install, and then you don't need to worry about whether the libraries are needed to support that or not. So this is pretty good. And then there is a huge development going on in this area. So I hope this discussion will give you some perspective on go and try something, and then try to write some chip design through OpenISA. All right, so with this one, I will conclude my lecture here. I wanted to talk about, for example, a pipeline implementation using Verilog. That's an implementation that we could see. But I will definitely share this slide with you, so that you could go and take it as a reference, and then go and then work. So this implementation was actually done in the MakerShip. So you could go and then just try to see how this was done. All right, so with this one, I will conclude here. Dr. Guzer, I will give this back to you.
Yeah, thank you, Professor. Thanks a lot. I think within a very short span, you have covered excellently about the Power 10 architecture ISA, and given the detailing about the memory clustering and all interconnects. Thank you so much. As well as the next portion, definitely my students will be more interested with that microwatt, what you have shown. That will be make them excited to work on to implement it on HDL, right? So thank you so much. So we we come to the end for our 10-hour collaborative teaching session. Thanks to Dr. Das as well as you for multi-core computing as well as open power architecture. And now, as per the schedule, will be something like this. We'll be having some 5-7 minutes to fill up the feedback as we did it for the part one. So that link will be shared by Dr. Das. At 8:55, my head of the department, Dr. Dhaval Pujara, he will be joining us for greeting the experts and vote of thanks. And sharp 9 o'clock, we'll be starting our special session by Dr. Peter Hopsey on OpenCAPI. So I request all the students to click on the link sent by Dr. Das in the chat and fill up the feedback for this 5-hour session by Dr. Gokarna Sharma on open power architecture. So I request everybody to take part and fill up the feedback, and once again be there in the meet for the session or what of things by Dr. Dhaval Pujar, our head of the department.
Dr. Gajjar,
And yeah,
I will answer one question by Ambika.
yeah,
Ambika,
please, you
yeah,
can do that in parallel. Yeah.
yeah, there are different EDA software and tools, but some of the tools, so when I sorted these tools, then there were previous versions and then the modified ones and everything. So if you go into the latest versions, for example, BSDL languages or the new, there is a TL Verilog and everything. So they are new tools, and then you can just pick those tools. And then, for example, MakerSafe is a new tool, just started not long back. So that is a tool. So if you look if you study a little bit into what are the tools that are available there, then you will get to know which one to pick and which one to not pick. And then of course we are here if you need any advice. So hope it helps you to pick those tools. Right. That also matters because all these EDA tools, what is happening is that now they are more streamlined, and then there is a company, and then they are trying to make them more unified and coherent. But before, everyone they were building their own tools. For example, you have a Verilog, the implementation, and then you extend Verilog to do something, and then that is there, and then after a while it was not maintained, and whatever facilities or the features that were there, and then they were just left there, and then you were using, and then when you need it, and then you again extend it, and then so there was no coherency. It was a little bit lacking. But now there are different companies started, and then they are making these tools more unified. So for example, MakerSafe, if you go there, that is well maintained, and then you can use it. Similarly, there are other tools available, and then some tools focus more on RISC-V, some tools focus more on Open Power ISA, some tools focus on other architecture. So you have to also keep in mind when you pick the tool, whether this tool is more focused on this particular architecture or that architecture. So that will also help you to make a decision.
Thank you. So I request once again all the students so that you fill up the feedback form, and if possible, keep your camera also. You can make it on. We'll be having one group photograph of all the participants if possible. So if possible, whenever I say, once our head of the department is there, to turn on your video so that we can take a snap of the group. Yeah, Dr. Das, you want to say something?
Well, first of all, I would like to thanks all the audience, and Dr. Gajjar, once again, thanks to you for inviting us, and all the students for listening to the lecture for these 10 hours and being patient and showing their interest for learning. So anyway, we are also interested to give them some little bit of certification for attending this course, and from that perspective we have actually arranged a multiple choice quiz. So I am sharing the link of multiple choice quiz in the chat window. So it's kind of an self-evaluating type of quiz, so the students can take their time at any point of time, and they can answer all the questions, and the form will ask their email ID, and I will get the email ID that way, and I will talk to Ganesan Narayan Swami, the Open Power lead, so that we can give the students as a certificate of participation. So please encourage the students offline, maybe after this course, to have the quiz so that they can get the certificate.
Sure, Professor.
And I will share the link with you again in offline in the email.
Yeah.
So Dr. Das, are we doing the quiz now?
Well, the quiz, possibly the students will do it offline, I believe.
Offline, okay.
Yes. We'll be doing it at a later stage because we are crunch of short time.
Yeah, so let them do that afterwards, and possibly it will go with the flow, because this is a very short 10 hours compact course. So let them go over the materials once again, and then they can have these,
Yeah.
or have the quiz.
Yeah.
And that way possibly they will learn much better.
That sounds good.
Yeah. So now, are we waiting for the principal?
Yes, the student
Sure.
has filled up
Yeah.
the feedback. So Ganeshan is going to join at 8:50. That's what he said.
Okay,
Mhm.
sure. And Dr. Gajjar, as I mentioned, like after, in the very end, possibly I will take another 3 or 4 minutes to do some promotional things for
Yeah,
Institute.
sure,
I will
sure.
just play one video, and that way we can conclude after that. Thank you.
I request all the students to be in the meet once you complete the quiz. Do not leave the meet, please.
Yes, because there will be another session also on the OpenCAPI and FPGA
Yes,
computing,
yes.
the overview. You can get the roadmap, like where the situation is moving in the hardware domain. So that will also be interesting.
So now we have with us Ganeshan also. So we welcome Ganeshan Narayan Sami, who is the key person for the networking for this particular collaborative teaching. Ganeshan, we welcome you. We have with us our head of the department, Dr. Dhaval Pujara. So, sir, we welcome you for this particular session. Hello. Dr. Dhaval Pujara, sir, we welcome you.
Thank you so much, Professor Gajjar.
Yes, sir. So, on behalf of Department of EC Engineering, Institute of Technology, Nirma University, I welcome all the two experts, Dr. Ardya Das from University of Wisconsin and Dr. Gokarna Sharma of Kent State University, as well as my friend Ganeshan Narayan Sami of IBM and education leader in Open Power. So, we have with us Dr. Dhaval Pujara. our head of the Department of EC Engineering. I request him to greet all the experts and the networking person and propose what of things. Over to you, Dr. Pujara.
Thank you so much, Professor Gajjar. At the outset, on behalf of the department and on my personal behalf, I welcome the expert speakers, Dr. Das from University of Wisconsin, Dr. Sharma from Kent State University, our expert adjunct professor from Austin, Dr. Peter Hofste. I also take this opportunity to welcome Mr. Ganesan Narayan Sami, who has played a key role for arranging this collaborative teaching. I welcome my colleague at the department who took a lot of pain in organizing this entire lecture series, Professor N.P. Gajjar. And last but not least, my very dear students who have been participating and getting a lot of knowledge, understanding from the experts, my dear students. So thank you to all the three experts and Mr. Ganesan. I was told by Professor N.P. Gajjar, and at the same time, I am in the email loop also. So I came to know the kind of planning that all the three experts have done for this entire lecture series. I must say it is amazing seeing all lecture slides, wonderful planning, the kind of project statements that have been explained by the experts. So I believe the student delegates have been benefited a lot by this lecture series. So from the bottom of my heart, on behalf of the department, on my personal behalf, I say thank you to all the three experts, Dr. Das, Dr. Sharma, and Dr. Peter. I also convey my gratitude to Mr. Ganeshan for playing a very big role in helping us arranging this collaborative teaching. Thanks are also due to Professor N.P. Gajjar, who is taking key interest in many initiatives of the department. Thank you, Professor Gajjar. I have a humble request to all the experts as well as Mr. Ganeshan that please be in touch with the department and please help us in organizing these kind of events. We have a wonderful department with almost 30 faculty members, and we are running a BTech program, 2 MTech program. Our MTech program as well as BTech program have been received by all our stakeholders with very good feedback and appreciation by industries, R&D organizations. We have got very good placement statistics also. But at the same time, we still want to strengthen our department by way of having experts in our panel of evaluation, our panel of deciding the syllabi, experts for delivering these kind of lectures. So I invite all the experts and Mr. Ganeshan to be part of EC family of Nirma University. I congratulate Dr. N.P. Gajjar and his entire team for successfully organizing this team. And I once again request all the experts, please be in touch with the department, and we humbly request that please guide us, suggest us, support us in all our endeavors. We really want to strengthen our department. Ultimate goal of the department is benefit of the students. We want to serve the society by way of providing the best engineers to the society. So again and again, I request all of you to please help us in serving the society in a better way. Once again, thank you to all of you. I cannot forget thanking to my own students who are who are part of this collaborative teaching. I believe they have been benefited a lot. Student friends, this is just a beginning. The course that we have delivered is again need of the day. Manpower is required in this field, so please try to focus on this field. And at the same time, the kind of project statements, today afternoon I had gone through an email by Professor NP Gajjar, and the kind of project statements that have been given to you, please, during your after your examination, whenever you find time, work on these problem statements, and I think that will pay you a lot in time to come. Once again, thank you so much to each and every one. Thank you so much, Professor Gajjar, for inviting me to talk to the speakers as well as to the students. Thank you so much.
Thank you, sir, for motivating us and guiding us all the time whenever we need you. Small request to all the participants and the experts to turn on your video so that we can take a snap for our memo. If possible, I request all of you to turn on your video if possible.
Please, friends, turn on your video so that we can have a good memory, a screenshot of today's session, and it will be a good memory for the department as well as for you also. I request all the students quickly so that we should not waste time. Everybody, please.
Yeah, thank you. Thank you so much.
Okay, sir, please continue. I'll take leave.
Yeah, thank you. Thank you so much. Okay, so Ganeshan, do we have Dr. Peter Hopsi with us?
I'm here.
Yes.
Yes.
Yeah.
Good evening, sir.
He's on.
And
Yeah.
to you, good morning. Thank you.
You're welcome. Good
Okay,
evening to you.
so without wasting time, I welcome Dr. Hopsi for this particular special session on Open Capi. Thank you so much for accepting our invitation, even in your tough time, uh, to talk to the students and motivating all of us. So it is my privilege and pleasure to introduce Dr. Hopsi. He is a veteran person for IBM and working on power performance. I know the students have always heard about the Sony PlayStation. He is the key designer for the processor for the PlayStation. So that's how he has started with the multi-core computing in the true sense with the application. He is currently a professor at TU Delft also, which is also top universities in the world ranking. So, sir, we are very much thankful to you, and it is very much important for me to mention that he is having a number of awards in the field of processor architecture. It is our privilege that we have with us Dr. Hopsi on this platform. Thank you, Ganeshan, for arranging this particular session. Thank you. So the floor is yours, sir.
Yeah. Thank you, Dr. Gajar. It's a pleasure to be here. And yeah, with the PlayStation 3, it was a very fun project to work on. I never know if I should apologize for all those people that spent too much time playing games, but it was certainly a fun project to work on. So today, what Ganesh-san and Dr. asked me to do was give a brief introduction to a different course that is available, and so let me do this. I hope this works. Okay, it's not. It doesn't seem to be happening. Ganesh-san, are you? Can you hear me?
I think you have to give the permission in the settings for screen sharing.
Okay. Yeah. Alternatively, Ganesan could perhaps.
Yeah. Can you,
If you. Yeah,
yeah,
you have the slides, right? So maybe if you can bring up the slides, that might go the quickest.
hold on.
They're in the Slack message, right?
Yeah, sure. 1 second. I'm just opening up Slack. Yeah, I got that. Hold on.
Okay, great. Thank you. So I'll just start talking. Dr. Gajar just referred to the PlayStation 3, right? So in the PlayStation 3, this is basically where we introduced the concept of heterogeneous multi-core computing, right? So we had different types of cores, different ISAs that were sharing the memory and the system resources between those different cores. So what we've done since then with CAPI and OpenCAPI is we've done the same concept, right, where you have different types of computational elements that share the memory, through virtual addressing, so that you can pass pointers between accelerators and the host CPU, rather than having to copy data for the accelerators to work on into buffers that only accelerators can touch. So we created with CAPI and OpenCAPI that same concept of a shared system memory between accelerators and host CPUs, but now extending beyond the physical boundaries of the chip. What I'm going to talk about here is some ideas that actually extend this even further to memory within a cluster of machines, right? A collection of machines that would run different operating systems. And the context here is that what is happening in the industry is that we're increasingly interested not in only large amounts of data, but we want to hold that data in memory, and we want to do very reactive type of computations on that data. And that really means that we like to have this data present in system memory. So if we go to the next slide. Yeah. So a lot of data. Of course, this notion of keeping data in memory is nothing new. I mean, most of computing kind of works that way. But it's the scale at which we do it, right? Across the cluster, that is somewhat different. Now there too, it has been done. There's been things like key value stores, like Redis, for example, or Memcached are examples. In memory databases. For example, DB2 Blue is an example of a database that holds data primarily in memory. SAP HANA is another such example. Even though in the case of HANA, it's in these cases it's largely restricted to a single large SMP. And there are even big data frameworks that are more memory oriented than storage oriented. So where Hadoop was really built around HDFS, I would say, Spark is built primarily around memory resident RDDs, but you can use those objects in memory within the Spark framework and not really across frameworks. So what is new in what we're looking at here is actually a notion of virtually addressed byte-addressable memory shareable between applications and across a system. So it's not just a file cache or a key value store or something like that. It's actually random access OS or multi-OS managed virtually addressable memory. So if we go to the next slide, please. I'm not seeing the next slide yet.
Not it?
No, I don't see it yet. I mean, I can. If you do see it, I can start talking to it. I do have my own copy. But,
Yeah. Please go ahead and start talking. Actually,
okay. So
like,
yeah. Now I see it. So of course, this kind of a change can give us some big benefits, right? So having random access to memory obviously opens up new possibilities. Being able to share data as it is in memory with virtual addresses and passing pointers avoids a lot of overhead in terms of serialization and deserialization. And there is no device memory involved here, right? So no copying into accelerator memory, in order to invoke an accelerator. The accelerator can work directly on data that's available in the system memory. But these benefits come with some big challenges as well. So we need in memory, right? So typically in the past, data in memory was thought to be touched by only one application at a time, and that application would decide what the format of that data was, and maybe it was in a file where you would worry about standardizing what the data looked like in a file, but not in memory. But now that we're going to have multiple applications touching the data in memory, we do have to worry about standardizing the layout of that data. There's a need for hardware standards to attach accelerators to host systems. And there's even more pressure on memory cost than there already is. Memory cost, DRAM memory cost, is a significant fraction of system cost today. And of course, wanting to hold even more data in memory puts even more pressure on that. And then last one here is that applications that tended to be I/O limited, for example, databases historically were limited by how many disks you had and how many random seeks you might be able to do on these disks. They now become compute limited because we've getting the data from memory and a lot of those I/O and network related limitations are out of the way. So what I'm going to do is I'm going to talk about each of these challenges and how we might address them. So for the first one, and I think that's the next slide. So the first one, I'm going to talk about a standard called Apache Aero, and I'll go into more detail in that in a little bit. But I think it's a good example of a standard format for data in memory that can be shared. For the hardware standards, I'll talk a little bit more about CAPI and OpenCAPI, but then also some standards that are coming up, like Gen Z and CXL in particular. I'll talk about memory inception on Power 10 and a prototype of it called Kinesis Flow on Power 9 that addresses the memory cost issue. And then I'm going to talk about the computation related challenges. And there, and that really points towards this other course. The way to address it is to make it easier to use accelerators and to develop for accelerators, and that's what the course is about. So if we next go to Apache Aero, there's the next slide. So Apache Aero is an Apache project, and as you can see in the top right of the slide, it's a very active project. There's about 50 weekly commits, and this is a project that's already, I think, 3 years old. So indeed, a very active project. It standardizes what column-oriented and immutable tables look like in memory. It's not as restricted as you might first think, because you can recursively define some of these structures, and the tables can also have variable length fields, right? So it's not just fixed length, straight up tables. And there are bindings for like a dozen languages, so that part is very, very good. You can you can program in many languages and get direct access to these data structures. And a fairly large number of projects has adopted Apache Arrow. So some of these, merely provide conversions from the Arrow format into their own native format and back. But some, like Dremio, which is a Spark-like framework, but built, on Apache Arrow data structures as a primary data structure. Fletcher, which we will refer to later, is an FPGA project out of Delft University that makes it easy to develop FPGA code that operates on data in these Arrow tables. It's not only about in-memory data. There are also related storage formats, one called Parquet, and kind of on the network formats called Aeroflight that provide efficient, either communication over the network or to storage of these Arrow tables. I'm sure that there will be other standards. Not everything, is properly represented as a column-oriented table, but I do think this is a very good start, and there are many different things we can do with it. If we go to the next slide, so there I talk about OpenCAPI, Gen Z, and CXL. So OpenCAPI is the standard that we introduced on the power systems, and there's actually two main branches to it. OpenCAPI 3.1 gives us the way to efficiently attach buffered memory, like buffered DRAM or other kinds of buffered memory. And CXL 3.0 or 4.0 in the future provides for the attachment of accelerators that can virtually address memory across the system. Actually, in the case of power architecture, it's effective addresses because we have two-level address translation. But that's kind of a fine point. You can think of it as virtually accessible memory. Gen Z is an interesting project that was introduced to make disaggregated memory possible. And actually, the Gen Z specifications have just been donated to the CXL project. CXL stands for Compute Express Link. And this is, the CXL consortium is one that many companies have joined, including like Intel and AMD and NVIDIA. And IBM is a member of that as well. And it looks like a lot of the concepts that were introduced on OpenCAPI are going to find its way into CXL as well. So there are three main profiles for CXL. CXL.mem is quite similar, I would say, to OpenCAPI 3.1, and defines, how you would implement buffered memory solutions. CXL.cache is very similar to our regular CXL. And then there's a third profile called CXL.io, which really encapsulates the older PCI Express commands within the new CXL format. And that one doesn't really have a direct counterpart with OpenCAPI. If we go to the next slide, so that talks about memory cost. So as I mentioned, memory cost is already an important part, in fact, often a dominant part of total system cost, and that only gets worse. So we're interested in sharing memory more efficiently across a cluster. And one mechanism that we can use for that is, again, something that derives from OpenCAPI. So if you look at what happens when say from an accelerator, I access the system with a virtual or effective address, then that address gets translated to a real address or physical address through the page table. And then based on which physical port, that particular address range, behind which port that is supported, it would be routed to a particular interface on the chip. So that really means that a CPU used this way is effectively a router, with the page table being the equivalent of a routing table. And if I take the data that comes out over one of these ports and translate the real address back to a virtual address that can be understood by a next system that I connect to, then I can actually even create multi-hop routers. And there's an open source project called Timesis Flow that was done on Power 9. So there are Power 9 prototypes of this technology in use in various universities and institutes. And in Power 10, that real to virtual translation was included in the CPU itself. So if we go to the next slide, you see an example of what we can do with this. This slide just points out that Power 10 is actually a pretty hefty router if you think of it as a router, right? We have a couple of terabytes of memory bandwidth and quite a few ports. So if we go to the next slide, the first example that we show here is if I have a cluster or cloud type organization where I have a number of servers that are connected to each other through this memory inception interface. I can now allocate memory from different servers to one of these servers. So for example, if I have a workload, in this case C is an example and B is another example, that runs on server B and C respectively, I can arrange, with the cooperation of the operating systems on the remaining nodes to make their memory available to those servers that need it. So now I can provision memory to, the average amount of memory that I need, rather than than having to allocate the worst case amount of memory within each server. So that's a substantial saving. I think a Google study showed that typically only about 40% of the available memory is effectively used. So if you do something like this, it's easy to imagine that you might achieve something like a 2x savings in your total memory cost. Go to the next slide. So in that case, there's other topologies possible. We can use one of our IBM scale-up systems that can support up to 64 terabytes within a single system, and use that and attach other servers to that one through this memory inception interface, and do a similar thing than what's shown in this slide. I guess the other slide is still on the way, and effectively use one big server as a memory server, right, and make these very large tables available to other servers. And we can also connect multiple of these very large memory servers together, as shown on the top of this slide, and create clusters with as much as 2 petabytes of addressable memory. And again, this is all virtually load store addressable memory. Now let me go to the next one. The last of these 3 slides here shows a multi-hop scheme. Oh yeah, one more. If you click one more, the multi-hop scheme that I explained, right? When you go to virtual, from virtual, to real, and then back to virtual. Actually, if you associate particular address ranges with particular servers, and you arrange your page tables accordingly, you can set up routing schemes across a server. But again, still here we're using load store instructions. Now, of course, the latency of your load is going to go up the more hops you take, right? With every hop taking, I don't know, maybe 150 nanoseconds or so. But still, that is a, it's a very, very large address space that you can get to this way. So now I think I will get to the talking a little bit about the course, right? So the final challenge on the next slide is, okay, if we have networking and I/O bottlenecks out of the way, yeah, and you can flip to the next slide. And by the way, all these slides are available. Ganesan can forward them to Professor Gajar. So now we're left with addressing the challenge of computational limits, and to address that, we're interested in accelerators. But accelerator design is not easy, right? So now let's look a bit at the course. So if we flip ahead. Okay, sorry, we have one more slide before the course. So I already mentioned the Fletcher project. So in that case, we have Apache Aero data sitting in memory, right, within the node or within the cluster. We have an FPGA that we want to use to operate on that data. So that orange bubble on the right is some kernel on the FPGA that is able to efficiently process data in these Aero tables. But usually there's a lot of effort involved in getting that data to the FPGA. So what the Fletcher project does is based on a schema of the, for the data in memory, and perhaps some attributes like how many data elements you want to see each cycle or things like that. It automatically generates the interface for the FPGA, making it far easier, to develop reconfigurable logic solutions, for this problem. So if we go to the next slide, so then turning to the course, and if we go to the one after this. And it's called Accelerating, Big Data with FPGAs and OpenCAPI. So we provide an architectural introduction first, and by the way, there are a number of people that have contributed to this course, right? So I only did a part of it. So first, an introduction and motivation, kind of similar to what I went over today, but in greater depth, as well as the motivation for acceleration on shared memory. Then an introduction into FPGAs. Ocxl is the framework that makes it easy to access FPGAs on OpenCAPI. So actually that Fletcher framework that I mentioned, its implementation on OpenCAPI is leveraging the Ocxl framework, and that framework is very nice. We have, we have the ability to simulate FPGAs alongside CPUs, just on your x86 processor, right? So everything that you need is packaged up into a virtual machine that you can download. And run. I think you can run in a container, and you don't need a system with an FPGA to be able to take this class and do the exercises. It's all there. Then we introduce Apache Aero, again, kind of similar like to what I have done here, but in much greater depth. And we go into a couple of application areas, particular acceleration for genomics, as well as a talk from the that addresses X-ray processing of X-ray data, both as two interesting examples of high performance processing on big data, with FPGAs. So I think it's it's quite a practical course. I hope it provides a good introduction to computer architecture, but it also teaches you how to program FPGAs, and we've tried to make it accessible to people who might have more of a software background rather than a hardware background, right? So of course, FPGA's kernels can be written in VHDL or Verilog, but more typically here they might be written in say C or C++ and compiled with HLS, and that Fletcher framework is used to generate the interface. Professor Das, who is also on the call here, he pulled all of this together. Thank him for having all of this available. And then I think that the last slide here just provides a bunch of links, where you can find this course. There's I don't know, maybe 20 or so segments of maybe 20-minute videos each available through the YouTube channel. There's a chat room. When you go through the course webpage, you'll find this a course execution environment that you can download. We hope that this makes this kind of work a lot more accessible to a wide audience. So with that, I guess if there are questions, I'll take them. I know that we're right at the bottom of the hour for you.
Yeah, thank you, Peter, for a very nice introduction, for making us aware and bringing our horizon wider. That okay, these are the different type of possibilities in terms of big data analytics, accelerator design, as well as putting it on the FPGA. And as this is something new which the university doesn't offer, that you have put it into the open courseware and maybe offered by institute. Thank you so much for letting us know about this particular aspects. And I have one small question. As you mentioned that FPGAs are being simulated on the virtual machine platform on the x86 architecture. Later on, suppose it is to be brought on an actual real FPGA. Are there any possibilities?
Yeah, well, I mean, we do have Power 9, and a number of institutes, have acquired these systems, and these kinds of accelerated Power 9 systems are running in a number of different places. I think in Oregon they have some of this infrastructure as well. I don't, we had a Power 8 or might still be there at the University of Texas that was used by people worldwide, at a low cost, or actually at a no cost. That was free. There was also a cloud provider that provided it. It's a little tricky to say, right? Because we have no idea how many people would sign up for this course. So what I would say is once you have a project and it runs within the simulator, it invariably runs on the actual hardware, right?
Why I'm asking a question is, recently we participated in Xilinx Adaptive Computing Challenge 2021, but that
Right.
I was not having much idea about the data center and AI. That was a part of one of the problem statement for that challenge. We participated for the Edge AI. We got selected for the next level. We are going to get hardware for KV260 from Xilinx for the Edge AI and vision application. But similarly, they have their Versal FPGAs for the data center and AI. So that's how I just ask a question.
Yeah. So again, I mean, we have made available some power. Well, a number of institutes have purchased their own Power 9, FPGAs. We've made Power 9 systems available to a few institutions that make them available to others, right? But it's a little difficult to gauge, what the scale of a course like this might be, right? So I think I would kind of turn it around. When people have developed a project that looks compelling, right, and made it all work on the simulator, and say, hey, I have a project here that I'd really like to run on some real hardware.
Yes.
At that point, if somebody reaches out, I would say they'll at least make an effort, to try and link you up with somebody, right? Either work with Oregon or some other place that has this hardware, to try and make sure that we can do it. But it's, I think the idea of providing the environment this way was to make it very easy and very accessible to a lot of people. Yeah.
Okay, yeah, thank you. Any question from the students?
Oh, and I guess I should mention the Fletcher framework is not unique to Power alone, right? So even though it runs more efficiently on Power, I think on Amazon EC2 F1, that's another place where you can deploy Fletcher based solutions. So it's, it'll run best on Power, but it can be run on non-Power FPGA accelerated frameworks as well.
Okay, thank you so much for spending your time to talk to our students, as well as being a special session on OpenCAPI. Thank you so much.
My pleasure. Thank you.
Wishing you a good
Professor Gajar.
and great day ahead.
All right. Okay.
Yeah.
Have a good.
Thank you. Thank you, Ganesh.
Have a good evening. Bye-bye.
Yeah. Thank you all. Thank you all for the wonderful session. Thank you.
Thank you.
Hey, hi, Dr. Gajar. I will possibly take another couple of minutes for the promotional.
Yeah. So we definitely thank you, Ganeshan, and Dr. Sharma. So thanks, special thanks to all the students for extending their working hours even after late evening, 7 to 9, where semester is ending, submissions, special assignments. A big round of applause for the students.
And today is a Friday.
Today is Friday, and for us in India, we have a Dev Diwali, so they have actually a off day and a holiday.
Yeah.
Oh, okay.
So,
all right.
Special thanks
for
to
being
students.
so patient.
Yes.
Yeah.
So another 5 minutes, we have this is a kind of, in the true sense, a collaborative teaching where we have 6 organizations: Department of EC, Institute of Technology, Nirma University, University of Wisconsin, Kent State University, then IBM, then Open Power Foundation, and Institute. So in the true sense, a collaborative 6 institute has the organization has taken a part into. Dr. Das is looking after our institute and trying to create some platform for the students and the community to learn the technical aspects of the new generation technology. So he is going to do a presentation for maybe another 5 minutes about the institute. So I request Dr. Das to proceed, please.
Sure. Before going to the presentation, I would like to thank you all, starting from Dr. Gajar for inviting us, to Ganesan for making this thing happen, and Dr. Gokarna Sharma for agreeing to do the presentation together with me, and Dr. Hofsty for the guest lecturer. And special thanks to Dr. Dhaval Pujara for coordinating all these things as the HOD of the department. So, well, I am not going to take much time, so I will just play one small video to show that why Institute is important and what is the major motivation. So just before going to the presentation, just one-liner. Here at the Institute, our major motivation is to make the data and technology education affordable and accessible and available to anyone, anywhere, and anytime. So in order to do that, we are collaborating with many organizations and doing all these things. So instead of wasting more time, so let me just play the video over here, and you can easily understand. And so here is my video. Hope you all can see. Technology is evolving. Can you all see this?
Yes.
Yeah.
Okay, perfect. All right. Every day, the jobs are changing at same pace. Learning the right tech skills to be productive is becoming harder and harder. Hilani got her bachelor's degree in electrical engineering, but landed up in a job at Data Power, a data analysis and IT company in the field of energy and power, where Hilani needs to develop several new skills. The life was stressful, learning new technologies all by herself and being productive at the same time was really, really hard. It started hampering Hilani's work-life balance. And Hilani is not the only one in this story. The entire Indian information technology workforce consists of almost 4.36 million people, among which only 215k students have CS or IT background every year. So that means almost 4.1 million skill gap is still there, which is counting up to 20x gap in required skill and the experts produced in the Indian IT market. So what will Hilani do now? How can she learn the new skills needed for data analysis and relevant technologies? How can she be productive very quickly? Thanks to Institute, Hilani registered to the Institute learning platform and developed the skill sets significantly quicker than she thought. I am Arghya Kusum Das, the developer of the Institute learning platform, and at Institute, our motivation is to make data, computer, and IT education available, accessible, and affordable to anyone, anywhere, anytime. With our proven pedagogical technique, live lectures, and hands-on experiences on cutting-edge hardware infrastructure, we offer the students the best education and prepare them very quickly, in weeks rather than waiting for months or years. We have strong collaboration with many different academic organizations and industry, which prepare our students with the right skill that the job demands in the current world. After 2 months of launching Institute, we got more than 150 registration already, and after a few sessions in the Indian market and teaching a few students, we got several great reviews which prove the credibility of Institute platform. So that's about Institute. Here, data education is one big data problem that we solve. All right, thanks for watching this video. And here just one thing I would like to mention. Right now, the Institute's total sign up is more than 1,000, not 150 anymore. So there are a lot more things that happened in the last few months. So that's one thing. And the other part is, well, Ganesan was saying me about the MCQ. So as I have told, I already shared the MCQ to the students, MCQ link to the students to the chat window, and I will also share with Dr. Gajjar. So possibly the students will do that offline, and once we will get all their email ID, we can give them some certification. Ganesan.
Yes, that's correct. Actually, students, I encourage all of you to, go and work on this multi-choice question and answer them. I'm expecting, a very good percentage. You all have to score, and that will be nice to have. And also, we will be issuing a certificate for every participant as part of this.
Thank you, Ganeshan, for a gesture that will motivate the students to work on this particular field. And I extend my
Yeah,
sincere thanks to everybody.
and one more thing I forgot to mention that actually, I do have some IBM and Open Power goodies. The top scorers for this MCQ, they, I would say like a 5 or 10, would get, the IBM goodies like T-shirt and pens and US pen drives and all.
Thank
So
you. Thank you.
try to work hard on that and score well. Suddenly you'll get a T-shirt like what I am wearing, with the open, the power. Okay.
Good.
Sure.
Wish you all the best for the test.
Thank you.
Thank you everybody. Thanks to all the students. Thank you to Dr. Gokarna Sharma. Thank you to Dr. Das. And we look forward for the future collaboration and communication. We'll be in touch with you. And regarding that project, Dr. Sharma, I'll share the details to you.
So Ganeshan, can we also do the test and get the T-shirts and goodies?
Oh, sure. No, yeah. you guys
the
deserve more.
lighter side. Yeah.
You guys deserve more than the
Ganesan,
T-shirt.
Dr. Gajjar, me, and Dr. Sharma. Whoever will be the best performer, he will get the T-shirt. How about that?
Yeah. You guys deserve more than the T-shirt. We'll take care.
No, thank you everybody.
All right.
Anyway,
Thank you, everyone.
thank you.
Take care.
So with this,
Thank you,
we
thank
come
you.
to the end for our collaborative teaching on multi-core computing and open power architecture. Thank you all participants and my stakeholders. Thank you everybody. Bye. Wishing you all
Thank you.
great day ahead and a great weekend.
Thank you. You
You
too.
all. Thank you.
Bye.
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 Bye.